All right. All right, let's get started. Today is going to be a little light on the math. We're not going to have super heavy examples today. It's going to feel a little bit like movie time, but I'll go ahead and tell you things, not just like starting today, but really sort of the way that we handle things in steel design, they kind of change a bit. We're going to be relying a little bit more heavily on some design aids in the manual. And a lot of our theory and a lot of our ideas are going to start to change because really the overall theme of what we do in steel design changes when we start talking about things in compression. Things in compression like to buckle. And so how we handle buckling and the concept of stability, it's way different from tension members and what we've been doing with connections, because even with tension members and connections, you don't have to worry about that instability. I mean, I can yank on something all day long and it's going to fail just when it yields or it fractures. And mechanistically, and when it comes to design, it's theoretically a lot easier. But with things in compression, it's a lot harder without a lot of these design aids. So we're going to rely a lot more heavily on the manual. So it's like you almost are, it's even more important to bring the manual. So what I want to do, though, is I want to go back to mechanics of deformable bodies. I know everybody remembers everything from this class by heart, but I want to go back and do a derivation that's important to what we're talking about with columns, and that's this derivation regarding buckling. Now, I talked about columns a little bit last time. You know, ultimately what we're going to find when we get into the math is that a column's capacity is defined by its slenderness, its L over R value. Am I allowed to bring that up? But in all seriousness, L over R is going to become very important. In fact, the concept of slenderness and how it relates to buckling is going to become very important. Ultimately, the more slender a column it is, the weaker it is. And that's a little bit new. We never really cared how long a tension member was in terms of its capacity. I'm sure we had this L over R limit, but it didn't really affect the tension member. Like if a tension member was 6 foot long, it didn't get weaker if it was 12 foot long. Well, that's the case with columns, and so that definitely affects things. Now, the derivation that I'm going to show you is not new. I mean, it's been around for a very long time, and it's very useful. I'm not saying that the concept of elastic buckling is not a concept that we can't use, but using it by itself is not enough. If you look at a real life steel column's capacity and you compare it against its buckling capacity, you'll think buckling is wrong. And I'll explain why and how what we do in the spec sort of accounts for the differences between theory and real life. But first off, let's go to the theory a bit. So I have a column. Here, let me full screen this. So I have a column, and it's pin-pinned. So you can think of it like a beam. The mechanics are essentially assumed to be the same. It's pinned on one end, pinned on the other, and we're loading it in compression. So I'm pushing on it, and I'm asking at what point does that happen? At what point do I start to lose that stability of the column and I undergo a sudden change in the geometry and it undergoes buckling? If you want a technical definition for what buckling is, it's a sudden geometrical change in the structure due to a load in compression. You're loading it, and bam, it suddenly bows out. That's the concept of buckling. And not only does it suddenly change in its geometry, its capacity and its stiffness drop like crazy. Now, what we're going to try and do is determine the load that causes buckling, the load that causes that to happen. Now, in order to do that, one of the things I'm going to do is I'm going to break out some statics. And so in order to do that, I've got my column in its buckled state. I'm going to cut a section. And when I cut a section at the column, I'm assuming that inside the column I have the axial load, you know, sum of forces in the y direction, everything going up's got to equal everything going down. So I'm going to have the axial load, but I'm also going to have a bending moment. I mean, the column looks like this. It's being bent, so there's going to be some bending in there. And I propose that bending, just based on the statics, equals the amount of load in the column defined or multiplied by its deflection. Okay, so the moment is a function of how much it's deflecting. More deflection equals more moment. And so that changes what our equation looks like here in a second. Now, going back to structural analysis, I know everybody remembers this because we saw this and we use this in structural analysis. The idea that the second derivative of deflection can be related to the moment. The second derivative of deflection is m over EI, or y double prime is m over EI for you Math 33 or 335 fans. Now, what we're going to do is this. We're going to substitute where it says moment, we're going to substitute this py. The negative is just from our sign convention. So we have y double prime is negative py over EI, and we're going to rearrange. Oh, sorry, we're going to rearrange. So put everything all over to one side, and then what I'm doing is I'm going to make a substitution. Instead of this term p over EI, I'm just going to rename it, and I'm going to call it alpha squared. You're going to see why I'm calling it alpha squared in a second. I could leave it as p over EI, but it just makes the math a little easier to deal with. And so I have a second order differential equation. I know everybody here loves Math 335, right? Now, there are a number of ways to solve this differential equation. I'm going to use the method that is that most engineering students are a fan of. We don't know what you're talking about, Dr. Mike, right? Nobody ever uses it. What is this? Yeah, I know. So I'm going to type in that differential equation, y double prime plus, I'll just use a, alpha squared times y, and there it is. It's already, it's a very common differential equation. So here's the solution right here. Now we could actually use some Math 335 and we could write, the characteristic equation, second derivatives become r squareds, first derivatives become r's, just terms by itself becomes constants. Solve for your roots. You have imaginary roots, that's sine and cosine conjugate pairs, right? How many have had diffie-q? Did you do that? Okay. Oh, goodness. All right. So, look, would you just agree with me that the solution to this differential equation is that? An arbitrary constant times the cosine plus an arbitrary constant times the sine. Okay, all right. So what we got to do is we got to solve for those arbitrary constants. So the calculus is over. It's over. We got through it. Okay, so we have two arbitrary constants. Now, here's my column. I'm taking my column and I'm loading it in compression. But remember, this was pinned and this was pinned, and so it's going down like this. I propose that if the deflection is left to right, I propose that the deflection at the bottom of the column and the deflection at the top of the column is 0. So remember, I've got two unknown constants. I need two equations to solve for those constants, two boundary conditions. And so here's my two boundary conditions. Let's use the first one. So here's my equation. I'm going to plug in 0, set it equal to 0, solve for my constant. That's easy. Okay? Everybody okay with that? I mean, I know it's pretty fast, but C1 times the cosine plus C2 times the sine. My first boundary condition is that when x is 0, y is 0. So make that 0, make that 0, make that 0. The cosine of 0 is 1, the sine of 0 is 0, and there we go. The second one's a little bit of a different story, because if this is all 0 and I plug in x is L, I get this. Well, what do I do with that? That's a little different. The first one was easy. I got C1 equaled a pile of junk. Well, that isn't really the case here. I have this equation, and now I have to think about it. Engineering says we have to think about it. Well, let's look at this equation for a little bit. Okay, this equation, it seems innocuous, but there's a lot going on. Okay, let's just look at this as if we were pure mathematicians. Okay, I have C2 times the sine of alpha L equals 0. Okay, what are some ways that this equation could be true? Well, I'll give you one. One way that this equation could be true is if L equals 0, right? Because if L equals 0, then the sine is 0, and that's true, right? But that doesn't make sense physically, because for L to be 0, the column has to have no length, right? That doesn't really tell us much, okay? The constant could be 0, but if the constant is 0, if C1 and C2 are 0, if that's my equation, and this are 0, it would indicate that the column isn't deflecting at all. Well, that isn't the case because take a look at it. It's deflecting, right? Well, what about alpha? Could alpha be 0? Well, remember alpha squared was P over EI. So if alpha equals 0, basically that's a roundabout way of saying that there's no load on the system. Well, if there's no load on the column isn't going to buckle. So that really doesn't make any sense. But what about this? Remember the zero product rule? If you have A times B equals 0, either A is 0 or B is 0. What about the whole sine function? Could the whole sine function equal 0? Maybe that's not so trivial. Remember, if I graph the sine function, it looks something like that, right? Where does the sine equal 0? It equals 0 at integer multiples of pi, right? At pi, 2 pi, 3 pi, 4 pi. So this term inside the sine, this alpha L, if it equals integer multiples of pi, that's actually a not so trivial solution. So what I can do is I can say, well, if that alpha term equals this and alpha squared equals that, I could set those terms to equal to one another and solve for P. That's basically it. That will tell us the load that causes the column to go like that, because we assume that when the column buckles like that, it buckles like a sine wave. And so one of the things you'll find if you actually study stability, there's a lot of trig that shows up, a lot more than you would think. Yes? That's a good question. N's just integers, because where does the sine equal 0? At like 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, just integer multiples. Now, that doesn't mean much physically. Like, what does n mean when I take the column and I do this? I'm going to answer that very quickly, okay? So we have an expression now that'll tell us what the column looks like when it deflects and what the column's load has to be to cause it to deflect. So what are those n values? Physically, they're called buckling modes, okay? So what that means is this. Remember, it's a sine function. If you graph what does the column look like when n equals 1, it looks like this, okay? And the load to cause that to happen would be this value. If n equals 2, then the column doesn't buckle like this. It sort of like buckles like that. And for the column to buckle like that, the load would have to be this. For the column to buckle like this would have to be the load. The nice thing about this theory is that all you have to do is take a column and look at it. I would give anybody in this room like $1 million if they could take this column and their hand and push it and make it look like that. It doesn't work. When you take this column and push it, it's just going to buckle like that. It's just going to buckle under this lowest buckling mode. So what is the real life buckling mode? It's that. So I propose that the theoretical load that would cause this column to buckle would be this, would be pi squared EI over L squared, okay? Now, here's another thing. That's a critical buckling load. What about a critical buckling stress? Well, stress is P over A, and so what I've got is pi squared E I over L squared. I can factor out the I over A. I over A has a very specific name. We call it a radius of gyration. R is the square root of I over A. Well, it showed up again. This is from Engineering 216. I love my job. All right. All right. I know you're not making it up. Let's move on. Okay. All right. So let's get back to this. So Everybody watch up here. Everybody watch up here. So here's our buckling load. We can compute a buckling stress, and when we compute a buckling stress, what we're doing is dividing this by the area. And I over A, that's just a new section property, because if you have a shape, you should be able to determine the area of that shape and the moment of inertia of that shape. So the radius of gyration is just the square root of this value divided by this value. It's just another property of that shape. The reason why it's a valuable property is because when you start rewriting your equation, doing a little bit of algebra, you end up with this term here on the bottom, this term L over R. L over R has a very specific use in structural engineering. It's the term we call slenderness. The more slender a column is, the weaker it is. Now, like I said, Euler buckling is not the final answer, but there are some very useful observations. This term L over R, if L over R gets bigger, what happens to the column's capacity? If this value gets larger, what happens to this? It goes down, right? And so this is what I was talking about. This column has a certain length, and this shape has a certain radius of gyration. So L over R would tell me how slender this column is. If this column got twice as long, would it get stronger or weaker? It would get weaker. It would actually get 4 times as weak, right? Because it's L over R squared. So slenderness is a very, very critical topic, and identifying appropriate slenderness values is going to be very, very important for the next little bit, especially with columns. Now, there's a couple things that are immediately wrong with, let me say this. It's not really that it's immediately wrong, but if we just said that this was the equation, that's it, we never had to look at everything again, there are a couple things that we need to address. The first thing that we need to address is our boundary conditions. Okay? We assumed pinned on the bottom, pinned on the top. But you know enough about structural analysis to know that that's not always the case. Okay? What if you have that? What if you have a column that's fixed on the bottom and free on the top? Maybe something like a light pole in the ground, where you have it cemented in the ground and it's just free up top. Well, how can we use this theory for a column like this? Okay? The answer is we introduce this new term called K. Okay? K is what's called the effective length factor. And basically what we're trying to do is we're trying to map any random column to this. Okay? So K for a pin-pin column is going to be 1. And the reason why is because that goes from inflection point to inflection point. Remember, this is a sine curve, so it goes on forever. So that's the point where the curve goes from like that to like that. Remember, in math we call that an inflection point. You remember that? So if I have a column that's let's say fixed free, well, for it to represent a pin-pin column, I would argue that its effective length would look something like this, and it would probably be something like twice the original length, because that buckled shape looks like that one. Everybody okay with that? So whenever you have a column that's, let's say, fixed free, the effective length factor is theoretically 2, because doubling that length will generate the same buckled shape that you get for a column like this. Does that make sense? So that's what an effective length factor is trying to do. It's trying to map the deflected shape to look like a pin-pin column. Where can you find them in the manual? On page 16.1-570. Now, just so everybody is aware, that's way in the back in the spec. Particularly, it's in the gray pages. It's in the commentary. Okay? So it's right near the end of the commentary, 16.1-570. Okay? You're definitely going to need a tab here. Uh-oh. Uh-oh. Did everybody bring their AISC 15th edition steel construction manual? There we go. There we go. It's looking pretty good. We're almost there. All right. That's all it takes is just one day. And everything's come crumbling down. All right. So we're on 16.1-570. Does everybody see a table that looks something like this? Okay. So these are approximate values of effective length factors. Okay. Now, one of the things I want to point out about this table, first off, this is a tabbed page. You are going to be referencing this a lot. One of the things that I want to reference and make sure that everybody sees are these two rows down below. So there's one that says the theoretical K-value and one that says recommended when ideal conditions are approximated. Remember, there is no such thing as a support that's perfectly fixed. That's just a mathematical construct that we define to make analysis easier. But in real life, nothing's perfectly fixed and nothing's perfectly pinned. So for instance, if you have a fixed column, the theoretical K-value is 0.5, but that is not what you use in design. We bump that up a little bit to account for those theoretical or those irregularities between theory and practice. So the K-value right off the bat we're going to get here. Now just so you know, there's if you look on the next couple pages, there's these like weird looking charts. There's like two of them. There's one on the page, and if you turn it, there's one behind it. We're going to use those to determine K for if you're trying to look at columns in a braced frame or a moment frame, as opposed to just a single regular old column in a building that's holding up the gravity load. But don't worry, I have an aid that I'll print off for you where it blows those charts up a bit and you can draw on them a bit. But yeah, so just be aware we're going to reference that quite a bit. Now, there are some other minor assumptions that we're just assuming is the case, which is pretty easy to handle. For instance, we're assuming that the column is loaded directly through the centroid, and that can be handled just to ensure that can be handled with proper detailing, or you can look at beam-column interaction to handle if it's not loaded through the centroid. And as long as it's not twisting or shearing or anything like that, these equations would be fine, and that's not really even a major concern for W-shapes. However, if you were to just use the equations right now, I promise you they wouldn't work, okay? And there are two major reasons. Two major reasons. Nudge, nudge, wink, wink. I don't know how much clearer I can make it. Why real column behavior deviates from ideal column behavior. Exam. What? I didn't say anything. And that is the presence of geometric imperfections and the presence of residual stresses. Now, I'm going to explain each of those in pretty significant detail, but there is a reason, there are two reasons why what I've derived and what I've shown you thus far is not enough. And these are the two reasons. Residual stresses and geometric imperfections. That got everybody's attention. You're like, it's cold, it's Friday, we won't be here. Exam. Let's get out the highlighter. I know things. All right. So let me explain why. Let's start off with residual stresses. First thing I want to do is I want to look at this graph. So what I'm doing is I'm graphing on the x-axis, I'm doing KL over R, and on the y-axis this. So basically, if I was looking at the equation of the line or the curve, it would be like y equals some constant times x squared. And so if I graph y equals some constant, or not times, divided by x squared, if I graph that, that's a hyperbola, right? Right? So this is the graph of a hyperbola. So the problem with this graph right off the bat is theoretically, if I had a column with zero slenderness, it would have infinite capacity. That's not real, right? At some point, the column capacity has to be capped off a bit. So we're going to cap it off at Fy, okay? That I don't care how stocky the column is or how compact it is, compact sort of being the opposite of slender. I don't care how compact it is, I'm going to cut the capacity off at the yield stress, okay? And so I could, for instance, figure out where those intersect, just solve. That's a pretty easy solution, okay? So that would be one way of improving the accuracy, but there's a couple things that we need to address. First off, let's go back to our stress-strain curve. Stress-strain curves aren't perfect. It's not like linear yielding. They usually like round off a bit, like it sort of eases into yielding. Remember, there's like a proportional limit. That's where the onset of yielding occurs, and then Fy is when it's full-blown inelastic, right? So there's a little bit of a transition between those two. And so If you see me introduce this term, the E sub t, the tangent modulus, that's the slope in this region right here. But that really doesn't answer the big concern, and that's residual stresses. So first off, I did want to address inelasticity, but here's big ticket item number one, residual stresses. What's the deal with the residual stress? Well, the short answer for what a residual stress is any stress that is locked in to an element or to a component from the fabrication process. So let's go back to how would they manufacture like a rolled I-beam? Like how would they manufacture this? So you've got this big pool of molten metal, right? You cast it into a big like steel billet, like a steel near net shape, and then they place it under those super high capacity rollers, and they sequentially flatten this plate and flatten this plate a few times until you get a shape that looks like this, right? But then what happens to the I-beam or to the W shape? It cools down, right? You got this really hot shape and it cools down. Well, the problem with that is this actually doesn't cool down at the same rate. See, think about thermo. Oh God, I'm bringing up thermo to a bunch of civil engineers. Wouldn't it make sense though, just from basic common sense, that if I heated this thing up to like 2,000 degrees and just set it down, wouldn't it make sense that the tips right here, that they would cool first, and then maybe this would cool? What's the last part that's going to cool? Say what? I can't hear you. Where they come together, right? This flange web junction right here. This is going to cool last, whereas the flange tips and this web region right here, that's going to cool first. Okay. What happens when you produce I shapes is this: because it doesn't cool at the same rate. I mean, when things cool, they contract. When things heat up, they expand. Well, because it cools differentially, you actually lock in stresses in the W shape. It's almost like as it's cooling, it goes, and it's got these stresses locked into the shape as you get it from the mill. Okay. Now, we never really cared about this with tension members, because with tension members, there was never a stability issue. When we have gross section yielding, we assume we blow through all of this. But in actuality, there are stresses locked into the shape. Okay. Now, here's the thing. These flange tips right here and this center region, they go into compression. Whereas the regions where the flange and the web come together, they go into tension. Keep in mind, that load is already there inside the shape before you load it. So imagine I have this shape and I put load on top of it. What happens is this, okay? So you can actually start to yield, let's say, the flange tips in the center before you yield, let's say, the web. So as you're loading it, not only is it wanting to buckle, but certain parts are yielding before others. So not only is the shape wanting to buckle, but it's getting weaker and weaker and weaker because it's wanting to yield. See, here's the stress-strain curve of a normal, let's say, I shape. This is what happens when you load it in compression. As you load it, the yielding starts to penetrate throughout the section, so the section gets weaker and weaker and weaker, and it wants to fail at lower and lower and lower loads. So the real stress-strain curve is a lot more gradual than you would expect because of those locked-in stresses. In tension, we don't care about this effect. We assume gross section yielding is all the way out here. We don't care about residual stresses because there's not the buckling phenomenon. But here, it buckles. That's a bad day. Yes? That's a great question. The AISC column curves I'm going to show you, they take this into account. So the short answer is you go down to Lehigh and you go test about 500 columns and you match a curve that fits the data. So that's the short answer. But what I'm getting at is Euler buckling and that equation I derived for you didn't account for this at all. And this is complicated. Okay? But that's the first complication. The second complication, well, first off, anybody have any questions about this? Okay, this is the first complication. Here's the second complication. Nothing in this world, if we're talking about a column, no column in this world is perfectly straight and perfectly plumb. That's impossible. When you produce a column, directly out of the mill, if you take it, go like that, there's a little bit of imperfection. It's going to sweep a little. It's going to have some initial camber. That's just the facts. Instead of it being perfectly straight, it's going to have a little bit of bow. Okay? That's just the facts. Well, that initial curvature is really going to affect the capacity. Think, here's this column, right? And I load it until it buckles, right? But let's say I gave you the column and it was already bent like this. That's going to be a lot weaker than if it was perfectly straight, right? Make sense? So those imperfections have to be accounted for. See, the code allows you to have some out of straightness and some out of plumbness when you're constructing. For instance, when you're erecting columns in a building, yeah. That's a good question. The difference between, that's a great question. So the difference between the camber that you induce in a bridge versus the initial curvature that you get in a column is that the camber in a bridge is desired. You know that the beam is going to deflect downward some, so you're bending the beam up to get rid of that. But a column, you don't want that column to have a little bit of bow, because if you put people up here, whoo, that's bad. You don't want that to happen. But the now, are we talking about beams or columns, just to be clear? Okay. No, this is a fair point. Let me say this. You're never going to get something that's perfectly straight. Now, when would you ever order a beam that's perfectly straight? The simple answer is when the dead load deflection is just really tiny. Like if you calculate the dead load deflection and it's only like 1/10 of an inch, don't worry about it. So that's a good question. But yeah, with columns, we don't want them to be imperfect, but they are. See, here's the easiest example I can think of. And what ends up happening with imperfections is you get what's called, so here you basically get what's called a second order effect. Here's the easiest way to describe a second order effect. Let's say I'm standing on top of a hill and I have an 80-pound backpack on me, okay? And let's say Sam doesn't like me very much, and he decides he wants to give me a shove, okay? Well, one thing holding the backpack is, I'm holding it like this, but what happens when he shoves me? Well, not only am I holding this 80-pound backpack, but now I'm holding it with an eccentricity because he shoved me, right? Well, more eccentricity equals more moment. More moment means more deflection. Means more moment, means more deflection, means more moment, means more deflection. Everybody see how it kind of builds on itself? That's what's called a second order effect, okay? And that is particularly pernicious when you have an element that's subjected to compression, because the more compression and the more moment means the weaker it's going to be. It's sort of like what happens when you get that whoa, 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 whoa feeling, because it sort of builds on itself. Well, that's what happens with columns if you have that second order effect. And so if you take that second order effect and combine it with residual stresses, you can have some pretty significant reductions. So the question that Ashton asks is, well, how do you account for all this? Well, you certainly don't account for it by trying to derive an equation, okay? That's difficult, okay? What you end up doing is this. Back in, 50s, 60s, what have you, go down to Lehigh University. Steel industry gives Lehigh about 500-600 columns of different lengths, different shapes, different what have you, and they just test them all to failure, collect the data, and find a curve that best fits the behavior as close as possible. And what ends up happening is you get a curve that looks something like this. So, excuse me. So this is, what I'm showing you right now is a plot of what's called the AISC column curves. So first off, we never had to worry about anything like this with tension members, because we never had to figure out, like we didn't have to calculate what the limiting stress is. If it was gross section yielding, the stress was Fy, and that was it. If it was net section fracture, the stress was Fu. That was it. Whereas for columns, it's a little bit more complicated than that. So the first thing that we have to do is recognize that the column's capacity is a function of its slenderness. The more slender a column gets, the weaker it is. Okay? So just so you're aware, see this little thing right here? That's that cutoff curve I showed you before. But in reality, the capacity is reduced a bit because of imperfections and residual stresses. So first off, this dashed curve is the theoretical one, but really we're after this solid lower curve. Okay. And the second thing is, as the curve gets longer, the capacity gets lower. Yes?
Like in the field, if you were inspecting the job, how can you tell for sure if it's the imperfection is too bad to use?
That's a good question. So the question was, how can you tell whether or not the imperfections are too bad? So when you're erecting a structure, the code has certain tolerances. Like, have you ever heard of machine tolerances? Like you can't fabricate something perfectly, but what you can do is fabricate it within plus or minus 1/10 of a millimeter, or plus or minus, 1/100th of an inch, or what have you. Well, when you're erecting, let's take the pharmacy, the new pharmacy building. That was a steel frame. If you think those columns were erected perfectly plumb, so the difference between plumbness and out of straightness. So here's a perfect column. An out of straight column would be like this. An out of plumb column would be leaned over. Okay? The code allows you some wiggle room for out of plumb, because you're not going to erect something that's perfectly plumb. But what you can do is erect a column that's within code limits. So a typical plumbness limit is h/500. And so to give you kind of an idea, if you have a 12-foot column, that's about 1/4 of an inch. So think, a column that's 12 foot long, we're allowing you like 1/4 of an inch off. That's a pretty realistic, expectation. So you're going to have the total station, you're going to have it set up, right? You're going to bring the prism rod, not the leveling rod. Some people heard that, some people didn't. So you're going to have the total station and the prism rod. You're going to shoot the column and make sure that it's within tolerance. If not, you're going to use come-alongs or something like that to get it where it needs to be. So the short answer is you just have to measure it and make sure that you're within spec. So. Yes. Yes. Yep. Make sure you have your total station and your prism. Need those two together. Okay. I didn't say anything. Okay. Now, okay. All right. Is everybody okay with the idea that the more slender a column gets, the weaker it gets? So as this slenderness value gets larger, the capacity ultimately goes down. Everybody okay with that? Now, what we do is we split this up into actually two regions. And so the way that this works is this. If you have a column that is really, 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 really slender, like really slender, what ends up happening is it's not the residual stresses that govern the capacity, it's the imperfections. So in that region, elastic buckling ends up governing. And so what you do is you end up taking that elastic capacity and you multiply it by 0.877. And so that's the elastic range of buckling. Most of the columns that we're going to deal with are going to be inelastically buckling columns. And columns that buckle inelastically, their capacity is computed as follows. And so if you open up Chapter E, which is on 16.1-35, if you open up Chapter E, so you'll note it should be right near your shear lag factors. Remember, shear lag was Chapter D, design of members in tension. Chapter E, design of members in compression. So first off, the capacity is determined by taking this critical stress and multiplying it by the area. And then the phi value is 0.9. The area is easy and the phi value is easy. The problem is determining the critical buckling stress. And so let me explain how this works. What you're going to do is you're going to compute a slenderness. And you're going to compare that slenderness against this value, 4.71 times the square root of E/Fy. So that's on the following page. And so why? Because if you take this equation, set it equal to that, and solve, that's where these two equations meet, is that slenderness value. And so if your slenderness value is less than or equal to this limit, you're in the inelastic range, that's your capacity. If you're greater than that, you're in the elastic range, And that's your capacity. And so it's a pretty straightforward calculation. In fact, when we have homework 6, the first problem is that I'm going to give you a material, like a yield stress, and I'm actually going to have you plot this in Excel. So get your plotting, graphing abilities in Excel, get them sharpened. Okay, this is something I want everybody to make sure that they're paying attention to. See this right here? This is 0.658, and it is raised to this fraction. This is an exponent. So you take Fy divided by Fe, and if that was 2, it'd be 0.658 raised to the 2, not 0.658 times 2. So make sure that you're aware that that's an exponent. That's not, you're not multiplying by that fraction. That's a very easy mistake to make when you're first doing this, that's a multiplication. It's an exponent. It's raised to that fraction. Okay? Now, if you open up the spec and you look at these equations, you're going to see this term L sub C pop up. Does everybody see this? L sub C? L sub C is just the code's way of calling this KL. So if you see me, I'll be honest, I might ignore it and just write KL quite a bit. Just forgive me, but KL and LC are the same thing. And like determining what LC is and determining how to compute that is actually going to be a very big topic of discussion. But I'll go ahead and tell you the reason why the code is calling it LC is because there is a similar L sub B for beams. So they're trying to use notation that's somewhat similar so that you understand what's going on. Okay. The other thing I'll mention is that this term F sub E that keeps popping into these expressions is the Euler buckling term. I would stress that you pay attention to your units because you have a column length in inches, a radius of gyration in inches. So you need to make sure that you're using consistent units because L over R is supposed to be unitless. Okay? So it's just something to keep in mind. All right. Everybody with me so far? Now, what I want to do is I want to introduce another sort of related topic to columns and beams. We are going to handle this concept very easily, but I want to make sure conceptually you understand what's going on. Now, does everybody see these two images here on the slides? Okay, this image here up top, this is, I'm cheating a little bit because this is from a fire that happened in London. Okay, and you'll notice something happened with the column. It's not like this where the whole column just sort of bowed out. That isn't the case. What happened with this is that it's not that the entire column failed, it's that the flanges failed. Does everybody see that? It's not global buckling, the entire column globally buckling about its axis. It's the local elements, the individual flanges that failed. Okay? This is what local buckling is, not the entire column failing, but the flanges or the web failing on their own. Okay? Now, this is from a fire in London. I'm just curious if anybody can guess where this is. It's a subway, New York City. I know, but when, why? This was under the World Trade Center. This was I have searched to try and find a better image of this column because it's a really remarkable example of like a physical instance of local buckling. But this was a column under the subway, and it's kind of hard to see, but you can see how we've got a little bit of that global buckling happening because you can kind of see that the column is bowing out, but you can also see that that flange is it's almost like a sine pattern because it's coming in and going out. Local buckling and global buckling, they pretty much both happen. Like if you take a column and you load it until failure, both are going to show up. It's really a matter of which one happens first. Is it buckle locally first or does it buckle globally first? Now, the way that we handle that is through a slenderness check, and I'm going to talk about that here in a sec. Now, I just derived for you the critical buckling stress for beams. You know, that pi squared E over KL over R squared. Well, that's for beams, for a one-dimensional element. Okay? Y'all remember in concrete design when we talked about one-way slabs versus two-way slabs? Remember that? So two-way slabs incorporate what's called plate bending theory, something that bends this way and that way. And the critical buckling stress for a plate is in no way, shape, or form something that I would expect you all to be able to derive. That is a pretty advanced concept. So I'm just giving you that equation down here. It's a function of E, it's a function of the Poisson's ratio, and how it's just B over T, how wide the plate is versus how thick it is. What we can do is we can take that width to thickness ratio and compare it against, well, what happens if the plate is fixed on one end, if the plate is pinned on one end, if it's free, if it's not, and we can get different sort of effective length factors as a function of those boundary conditions. So you can look those K values up. That you can find them in textbooks all over the internet, or textbooks or resources all over the internet. What we do for a wide flange or an I-beam or something like that is this. So we rearrange this equation a bit. I'm not going to make you follow all this math, but here, let me skip ahead to this, and I'll probably recap this next time. But what we do is we look at an I shape and we say, okay, we split the I shape up into two types of elements. One of them is an unstiffened element, and one of them is a stiffened element. So a stiffened element would be something that's supported on two sides, like the web, and an unstiffened element would be something that's supported on one side. So another instance of let's say, an unstiffened element would be like an angle leg. Like if you have an angle, each of those legs would be considered unstiffened elements. If you had a channel, the web would be considered stiffened, the flanges would be considered unstiffened. And for each of those different limits, what we can do is we can say, okay, this right here, it's somewhere between being a fixed end and a pinned end, so we'll just split the difference and say that's our limit. And if you look it up in the spec, you'll see that's exactly the limit that we're going to use. We're running out of time, so I don't want to dig too heavily into those details, because I'll sort of elaborate on that on Monday. What I do want to do is indicate this. Okay? So I want everybody to turn to 16.1-17, because we do have time for this. What's that? Yes, this is a new tab. Okay. The short answer, and we'll explain the theory a little later on Monday because I don't want to rush it because I think this is really important. But the short answer is what these ratios are sort of limits that tell us as the analysts whether or not we're going to have to deal with local buckling or not. And I'll go into the math a little later on Monday. Excuse me. But this is a very sort of critical section to tab for a couple reasons. One, if you look at the top of this table, it says width to thickness ratios, and it says compression elements, members subjected to axial compression. So the short answer is that B41A is the table for columns. If you turn the page, you have to deal with table B41B. B41B is the table that we will use later when we look at beams. So remember me telling you that columns and beams, they kind of go together? Well, this is sort of one of the instances where that's the case. So what we'll do, let me just say this, the actual math behind checking whether or not local buckling is going to be an issue is pretty easy. What we'll do is we'll review that the theory, though, on Monday, and then what we'll do after that is, just so everybody can see the future, we'll go through the procedure for column analysis. There's a couple different ways that you can go about it. And what we're going to do is we're going to have this singular example, and we're actually going to do it multiple times. So we have this same example. We're going to analyze it once using the equations, and then another couple times using some design aids that are available to us in the manual. Once you understand how to use those design aids, you'll be able to, design. So that's sort of where we're going. I don't want to rush some of this theoretical discussion because it's really, really important. And I'd rather take my time and make sure that everybody understands what we're doing. That's all I got. Y'all have a wonderful weekend. Try and stay warm.